So here we have a cylindrical tank with a height of 10 meters and a base radius of 5 meters, and it's half full of gasoline. How much work is required to empty the tank through an outlet pipe at the top of the tank? And then they give us the density. So let's go ahead and look at a cylindrical tank, and we'll label kind of what we know. The height is 10 meters, the base radius is 5, and it's halfway full with gas, and we're going to pump it out to the top of the tank there. So we know that we use an integral with variable force, and it's force times distance. And in this particular case, the force is because of the weight, essentially, and so our force is mass times acceleration, in this case mass times gravity, but we don't have the mass, but we know that mass equals density times volume. So to get our force, we're going to need density times volume, and then we'll need to multiply that by distance. So this is going to be an integral here, and we're going to put the density out in front. Oh, I still need the g on there. We're going to put the g out in front too, because those are both constants, and we'll deal with them later. All right, so we're going to do our setup, and we're going to have our axes be, our coordinate axes be here at the center, the bottom of the tank. And so we are going to be working for the y, pumping out from the bottom of the tank up to the top of the water level, which was halfway full, so that would be at 5. And then we're going to have a dy that's going to be part of our volume. To figure out our volume, we look at a cross section, and if you see a cross section, it's going to be a disk. So it's going to be pi r squared multiplied by its thickness. So the dy is the thickness, but we do need pi r squared, and the r was 5, and it's 5 all the way up. So that's just going to be pi r squared, and then there was the dy for the thickness. So we now have volume in there. We have all of these pieces. So we have the force, but we need to multiply that by the distance. It needs to be pumped. It's being pumped to the top of the tank, and so right here, this total distance is 10. The water at the bottom, very bottom of the tank, needs to go 10, but the water right here in the middle only needs to go 5, and then everything in between right here. And so that could be expressed as 10 minus the y value wherever the slice is. Now we have force times distance, and we're ready to go ahead and figure this out. So in order to do that, I'm going to move the things that are constant out in front, which would be the pi and the 5 squared. So out in front, I'm going to have 25 pi rho, which is the density, g, which is the gravitational constant. And then with those out in front, I'm left to integrate 10 minus y. So I'll go ahead and integrate it while I'm doing this step. So that's going to be 10y minus 1/2 y squared, and that will need to be evaluated from 0 to 5. So I've got 25 pi rho and g, and then putting in 5, that's 50 minus 25 halves, and then when we put in the lower limit of 0, those are both 0. And so that's going to give us, let's see, 25 halves. So this would be 100 halves minus 25, so that's going to be 75 halves. And then I'm going to go ahead and just come up with a decimal approximate for this after plugging in the pi, the rho, and the g. So I'm going to have, well, the 25 times the 75 would be 1875. That's over 2. And then we'll still just put pi for now because we'll use the pi button on the calculator. And then our density that was given to us, that's 737. And then our g, because we are talking about things in meters, that's going to be 9.8. So now we can find the work done. And it looks like a big long number here, so we'll put in 212.723. I'm going to go to the nearest joule, so that's going to be 1, and that'll round to 3, and our units would be joules, since we need the work unit, which is Newton meters, or or joules.